Today's objective is to talk about the ambiguous case, which comes from side-side angle. So what you saw with law of sines is that if you have angle, angle, side, or if you have angle, side, angle, you're guaranteed a pairing of a side and an opposite angle to use law of sines. Also, when we have side-side angle, we're guaranteed a pairing of an angle and its opposite side to use law of sines. But there are 4 different scenarios when you have 2 given sides and an angle opposite one of those sides. And so we'll walk through what each of those looks like. And we did look at this with congruence, so it should be a review, but we're also going to put some numbers to it, whereas before it was more abstract. And so if you take a look at case number 1, you have that the side opposite is bigger than the side adjacent. When you are given side-side angle and side opposite is bigger than the side adjacent, there's only one triangle that you can form, and so there is no need to worry about any other type of triangle that could exist given the side-side angle. And so you would treat this just as you would any angle side, for example, triangle, and use law of sines to get one triangle. So again, side opposite bigger than side adjacent, one triangle, use law of sines, and you're done. It's when you get to these other scenarios that you have to think a little bit more. So for example, if I have side opposite is less than side adjacent, you might get that the side opposite is too short to form a triangle, but you will not know that until you do the math. So if you take a look at the diagram in the bottom left-hand corner, I hope you can agree that we are given an angle and its opposite side, and that the side opposite, the 8, is less than the side adjacent to the angle, which is 14. And so it needs to be on your radar that we could have no triangle that exists, one triangle, or 2 triangles that exist, based off of the given information of 8, 14, and 73. And so what you'll do is you'll use the law of sines as you have been. So you'll set up sine of 73 over its opposite side 8 equals, and hopefully you notice here that side C is opposite angle C. And so we're solving for angle C. And if you cross multiply as you would any normal law of sines problem, and our goal is to isolate the C, hopefully it makes sense that you need to take the arc sine of both sides, if you will, the inverse sine, to isolate the C. And if you notice here, like even before we do any substitution into the calculator, 1.974 is not possible for sine, because when you look at sine, it's an opposite side over the hypotenuse. And the hypotenuse is the longest side in the triangle, so anything smaller divided by the hypotenuse should be less than 1. And when you plug it into your calculator will confirm there's an error. So when side opposite is less than side adjacent, there's the possibility to get an error, which means that no triangle exists. And so really the triangle looks like what we have on the right side of the paper and not what was given on the left side. And so you would simply write error or no triangle for your answer, and there would be nothing else to solve for. Another example when the side opposite is less than the side adjacent is that you get exactly one triangle, and this triangle is a right triangle. We worked with this as a hypotenuse leg congruence situation, and from here you would use law of sine as normal. You would plug in the question mark angle over its opposite side and set it equal to the unknown angle, which would be what'll turn out to be a right angle over its opposite side. And when you use law of sines and you solve for the angle, you'll get that the angle is 90 degrees. And then from there, to be honest, it'll probably be a special right triangle, a 45, 45, 90, or a 30, 60, 90. And so then the last example, when you have the side opposite is less than the side adjacent, is where we talk about the ambiguous case. And when something's ambiguous, it's unclear. And so the thing that is unclear is that we could have 2 different triangles result from the given information. Taking a look at the next page in the notes, this is an example where it shows you the 2 triangles that can result. And so I'm going to actually start with the diagram on the right here. If I'm given the side opposite, I'm given the side adjacent, and I'm given the angle that's opposite the side, one of the sides anyway, what could happen is I can use this side opposite, and I could technically move that like I would a hinge, and it would travel underneath that base, but then it would come right back to that base, and it would form an obtuse triangle. And so what results is, given the side opposite, side adjacent, and the angle, I could have the big triangle, which is really an acute triangle, with the side opposite, side adjacent, and the question mark, or I could have this obtuse one, where I still have the side opposite is that fixed segment length. I have the side adjacent is the fixed segment length. And then I still have that given question mark angle is fixed. And so again, it could be the obtuse one as labeled in the middle, where the side opposite, adjacent, and question mark are consistent with this triangle diagrammed to the left, which would be your example of an acute triangle, where again, just given the criteria of side adjacent, side opposite, and question mark alone, there are two different triangles by swinging that side opposite closer to the side adjacent in the angle. And so you'll see there's an example worked out on this page. I hope you can see from the diagram that we have a side-side angle where the side opposite is less than the side adjacent. And so it needs to be on your radar. We could have 0, 1, or 2 triangles. When I set up the law of sines, which is worked out here, and I solve for the measure of angle C, it's not an error, so we eliminate 0 triangles, and it's not 90 degrees, so we eliminate 1 triangle, which means it's a specific case of 2 triangles that exist. And so what that means is that I could have a triangle where the given angle C is 58 as diagrammed, or I could hinge that BC segment and I could rotate it clockwise to form the obtuse triangle that's drawn below here. And if you remember, the sine of an angle is equal to the sine of its supplement. So if I take 180 minus the angle that you get for C, then that's the other angle that could exist in this triangle where the 10.5 is fixed between the two, the 12 is fixed between the two, and the 48 is fixed between the two. And so what you would do is you would finish solving for the information in the triangle given 58.14. And so you'll have something like on the bottom left here where you're solving for angle B and side B then. Or you could have something like on the bottom right where you are using the supplement of the given angle, and then you would still solve for B by taking away A and C from 180, and then you would use that in the law of sines to solve for side B. This page is just one more example to show you how the two triangles might result. Again, it stems from having side-side angle where the side opposite is less than the side adjacent. Looking at the plugin, the setup for law of sines, when I solve for angle C, I didn't get an error and I didn't get 90 degrees, so that means there are 2 triangles. And so if you look at the diagram up here, I could have an acute triangle where C is 68.41, or I could hinge side BC and I could create this triangle where it's 180 minus 111.59. And again, it stems from sine of 68.41 is going to be equal to the sine of 111.59. And then the rest of the math unfolds at the bottom of the page. And so the takeaway before I ask you to do a couple specific examples is that if you are given side-side angle, there are 4 outcomes with the law of sines. One outcome is that if the side opposite is bigger than the side adjacent, you're going to use the law of sines. There's 1 triangle and you're done. If the side opposite is less than the side adjacent, then you could have 0 triangles, which is going to stem from an error on your calculator after using law of sines. You could have 1 triangle, which means that you're going to get a 90-degree angle after using law of sines. Or you could have 2 triangles where you're going to get an angle other than error or 90, and then you're going to have to account for an acute angle and an obtuse angle. On this page in the notes, nearly done, I want you to try to recognize when you're going to have to worry about even having these 0, 1, or 2 solutions, or if you can just use law of sines and be done when you finish solving for the pieces on a triangle. So for example, if you look at the first now you try some, I'm given A, I'm given B, and I'm given side C. If you're given 2 angles in a triangle, you could figure out the measure of angle C, and then I'd have a pairing of an opposite side and an opposite angle. So I could use the law of sines and I wouldn't have to worry about multiple solutions, so this is a 1 solution. Whereas if you take a look at the next one, I'm given a side and its opposite and another side, so this is side-side angle, and the side opposite the angle is 15. 15 is less than 18, so this is one where you would have to pay attention to what you get as a result from your law of sines use and determine is it a 0, 1, or 2 solution. And then the last one here, measure angle B, side B. So right there I have a side opposite situation. And then I have A. So when I look at the side opposite, 9, and I compare it to A, 8, opposite is bigger than the side adjacent, so that is going to guarantee one solution. There's nothing more to worry about. And then let's go ahead and try to apply it to the mathematical setting and make it a little bit more concrete. So in this scenario, I want you to try to be precise in drawing an acute angle for the measure of angle C, for example. And so I'm going to put C down here and say that that's 70 degrees. We'll go ahead and put A over here and B up top. Side A is opposite A, side C, and side B. And then I'm given 15 centimeters for side A, and I'm given 10 centimeters for side C. In this case, I have side-side angle, and when I am looking specifically at the numbers, I do have that the side opposite, the 10, is less than the 15. So side opposite is less than side adjacent. So this means I do have to wonder, are there 0, 1, or 2 triangles that result from this scenario? But you won't know until you try the law of sines. So from here, law of sine says sine of 70 degrees over its opposite side equals the sine of, it's going to be angle A in this problem, opposite 15. From here, cross multiply to isolate the A or begin that process. Right here, since I'm multiplying sine A by 10, I would divide both sides by 10. And then to completely isolate the A, I would need to take the arc or inverse sine of both sides in order to, as I just said, isolate the A. And so from here, if you substitute that expression into your calculator correctly, you'll get an error. So that means there's no triangle that exists. BA actually would not exist, like B would not touch A. And so you do not need to fill out the table, and you would put no triangle exists. All right, this final example, go ahead and look at the given information and draw an accurate diagram as best you can. So 65 degrees is an acute angle for angle A. I have 22 as a side opposite. 24 is side C, and B is at the other vertex. If you look at the given information, side opposite 22 is less than the side adjacent. And so we do need to wonder, are there 0, 1, or 2 triangles that are going to result from this situation? We won't know that until we set up the law of sines, so let's go ahead and do that. We have the sine of 65 degrees over 22 equals the sine of angle C, yet to be determined, over 24. If you cross multiply, divide, and take the arc sine, you should be plugging into your calculator, so math you're going to do. You should be taking the arc sine of 24 sine 65 divided by 22 to get C. And if you plug that in correctly, you get about 81.38 degrees. Now, since this is not an error like the previous example and it's not 90 degrees, this means that we do have 2 triangles that could exist given the information of 22, 24, and 65. So the triangle could look like the one diagrammed above where the measure of angle C is going to be 81.38 degrees, or if we kind of rotated that side BC and we kept the 24 fixed, we kept angle 65 fixed, and we kept the side 22 fixed. If we hinge from B, then we could form an angle down here at C that's going to be 180 minus 81.38. That's going to be the obtuse angle that creates an equivalent sine value to the 81.38 degrees. And so looking at the chart on the right, I could have that angle C is what I got, which is 81.38 degrees. Or you could have a triangle where the measure of angle C is 180 minus the 81.38. And I think if you do that math, you get 98.62 degrees. And then from here, solve for the measure angle B. So do 180 minus the given 65 minus the 81.38, and do 180 minus the 65 minus the 98.62 to get the different values of B. If you solve that correctly, you'll get 33.62 degrees for the top triangle and 16.38 degrees for the bottom triangle. And from here, it's law of sines to figure out side B in each triangle. So for the first triangle, the triangle I originally drew, I'm going to use that base ratio of sine of A over its side, and then set it equal to sine of angle B, 33.62, over its side, and then solve for B. Looking at the other triangle and looking even at the information in the bottom box, we would use the same sine ratio to begin, since the sine of A was fixed and the side A was fixed. But in this case, we would use the value for the measure of angle B, which is 16.38 degrees over side B, and do some math to figure out what the approximate value of B is.